Welcome to the Deep Dive. Today we're digging into something really fundamental, how our planet's surface, the continents and oceans, are constantly shifting.
It really is like a giant slow-motion puzzle, isn't it? Understanding how it all fits together, past and present.
Exactly. And for you listening, especially if you're prepping for the UPSC exams, getting these concepts straight is, well, crucial. We'll break down the big ideas, focusing on what you need to know.
Sounds good. So today we'll cover the early ideas, continental drift, then a really key discovery, seafloor spreading.
Okay.
How those led to the big unifying theory, plate tectonics. And we'll wrap up with a specific example looking at the journey of the Indian plate.
Great. So where did this all start? That idea that continents might actually move. I always think of looking at a map. Africa and South America seem to fit, don't they?
That's exactly where the curiosity began for many, that almost jigsaw-like fit. It's quite striking.
Yeah. So who first really suggests they might have been connected?
Well, way back in 1596, a map maker, Abraham Ortelius, he sort of hinted at it. And later, Antonio Pellegrini actually drew a map with them joined up.
Wow, that early.
Yeah, but the person who really developed it into a proper scientific theory was Alfred Wegener. Around 1912, he called it continental drift.
Right, Wegener. And he proposed this giant supercontinent.
He did. Pangaea, meaning all Earth. And it was surrounded by this huge single ocean, Panthalassa, meaning all water.
Pangaea and Panthalassa.
Got it.
And this didn't stay together?
No, Wegener argued it started breaking apart maybe 200 million years ago, first into two big chunks, Laurasia in the north and Gondwanaland in the south.
And those broke up further into the continents we know today.
Okay.
But it wasn't just the shapes fitting together, was it?
Right.
He needed proof.
Absolutely. The fit was just the starting point, and actually later on in the 1960s, computers showed a much better fit, not at the current coastline, but further out, at the edge of the continental shelf, about 1,000 fathoms deep.
That makes more sense, avoiding the effects of erosion and sea level changes. Okay, so the fit was one piece. What else did Wegener find?
He looked at rocks. There are these ancient rock belts, about 2,000 million years old, in Brazil that match up perfectly with similar belts in West Africa.
Like tearing a newspaper and matching the ripped edges.
Kind of, yeah. And also, the oldest sediments found right on the coastlines date back only to the Jurassic period. That suggests the Atlantic Ocean itself is relatively young, geologically speaking.
Okay, matching rocks. What about glaciers? I remember something called tillite.
Yes, tillite. It's basically rock formed from glacial debris. Now, you find evidence of a massive ancient glaciation, this specific Gondwana system tillite, in places like India, Africa, South America, Madagascar, Antarctica, Australia.
Wow, all over the southern hemisphere, even places that are warm now.
Exactly. The simplest explanation is that these land masses were once connected, clustered together near the South Pole, and shared the same ice age.
That's compelling evidence. Okay, what else? There was something about gold deposits, right, in Ghana.
Ah, yes, the placer deposits. Ghana has rich gold deposits in its riverbeds, but there's no source rock for the gold nearby.
So where did it come from?
The source rocks are actually over in Brazil. When the continents were joined, rivers flowing from Brazil would have carried that gold across to the area that's now Ghana.
Okay, so the gold trail points to a past connection. And fossils, too.
Fossils are a big one. Finding identical species of land animals or freshwater reptiles on continents now separated by vast oceans. It's hard to explain unless the lands were linked.
Any specific examples?
Mesosaurus is a classic one, a small freshwater reptile. Its fossils are found only in specific areas of South Africa and Brazil. Now, this little guy definitely couldn't swim across the Atlantic.
Right, impossible. So their presence on both sides strongly suggests South America and Africa were joined back then.
Precisely. Lemurs, too, their distribution across India, Madagascar, and Africa also hints at former land connections.
Okay, so Wegener gathered all this evidence, the fit, the rocks, the glaciers, the gold, the fossils. It seems pretty convincing. Why wasn't his theory immediately accepted?
The main problem, the really big sticking point, was the mechanism. How could these enormous continents possibly move?
Right, what force could push them?
Wegener suggested things like pole-fleeing force related to Earth's rotation and tidal forces from the sun and moon. But physicists calculated that these forces were just nowhere near strong enough.
Ah, so he had the what, but not the how.
Exactly. Without a plausible driving force, most of the scientific community remains skeptical, even with all the evidence he presented.
Okay, let's quickly recap continental drift. Wegener proposed Pangaea breaking apart based on evidence like the jigsaw fit, matching rocks, ancient glaciers, placer deposits, and fossils. But the lack of a convincing mechanism was its main weakness.
That's a good summary. And that lack of a mechanism is what makes the next part of the story so important.
Right. The discoveries after World War II, particularly about the ocean floor, which eventually led to seafloor spreading.
Yes, the post-war era brought new technologies for mapping the seabed, and what they found was, well, not what people expected. It completely changed the game.
And around this time, an earlier idea about what might be happening inside the Earth gained traction, didn't it? Arthur Holmes's theory.
That's right. Back in the 1930s, Arthur Holmes had proposed the idea of convection currents in the Earth's mantle.
Convection currents. Like heat moving things around.
Essentially, yes. He suggested that heat from radioactive decay deep within the Earth heats up the mantle rock, making it less dense, so it rises. As it reaches the top, it spreads out, cools, becomes denser, and sinks back down.
Like a giant conveyor belt system inside the Earth.
Exactly. And Holmes thought these slow-moving currents could be powerful enough to drag the continents along. But back then, there wasn't much evidence.
Okay, so that idea was out there. Then came the ocean floor mapping. What did it reveal?
It revealed huge underwater mountain ranges, the mid-oceanic ridges running through all the major oceans. And these ridges were volcanically active.
Mountains underwater with volcanoes. Okay.
They also found incredibly deep trenches, often near the edges of continents. And maybe the most surprising thing was the age of the ocean floor itself.
Oh, so?
The oceanic crust turned out to be incredibly young compared to the continents. Nowhere was it older than about 200 million years. Continental rocks, on the other hand, can be billions of years old.
That's a massive difference. Why would the ocean floor be so young?
That was the puzzle. More clues came from studying the mid-oceanic ridges themselves. They found that the youngest rocks were right at the crest of the ridge, and the rocks got progressively older the further you moved away on either side.
Symmetrically older on both sides.
Yes, perfectly symmetrical. And these rocks showed patterns of magnetic striping bands of rock with normal and reversed magnetic polarity mirroring each other across the ridge.
Magnetic stripes.
Yeah.
Like a recording of Earth's magnetic field changing over time.
Exactly. Plus, the amount of sediment covering the ocean floor was much thinner than expected if the oceans had existed for billions of years.
Okay, young rocks at the ridge, getting older outwards, magnetic stripes, thin sediment, and you mentioned trenches and earthquakes.
Right. The deep trenches were associated with deep earthquakes, while the mid-oceanic ridges had shallow earthquakes and, as he said, lots of volcanic activity. The patterns were starting to connect.
So how did all these pieces fall into place? This sounds like the setup for seafloor spreading.
It absolutely was. In 1961, Harry Hess put it all together. He proposed that new ocean floor is constantly being created at the mid-oceanic ridges.
How?
Magma rises from the mantle, erupts along the ridge, cools, and forms new oceanic crust. This new crust then pushes the older crust aside, away from the ridge.
Ah, like a conveyor belt moving outwards from the ridge.
Precisely. That's the spreading part. And to balance the creation of new crust, Hess proposed that older oceanic crust eventually gets destroyed, plunging back down into the mantle at the deep ocean trenches.
So ridges are where crust is born, trenches are where it's recycled. That explains why the ocean floor is so young.
It does. It provides the mechanism. Constant renewal.
Okay, quick recap on seafloor spreading. New ocean crust forms at mid-oceanic ridges, spreads outwards, and older crust gets subducted at trenches. This was the dynamic process Wegener was missing.
Exactly. And it paved the way for the final unifying theory.
Plate tectonics. This brought everything together, right? Continental drift and seafloor spreading.
Yes, around 1967, scientists like Mackenzie, Parker, and Morgan synthesized these ideas into the theory of plate tectonics. It provides a comprehensive framework for understanding how the Earth's surface works.
So what is a plate in this theory? It's not just the continents anymore.
No, it's bigger than that. A tectonic plate, or lithospheric plate, is a massive, rigid slab of rock that includes both the crust, either continental or oceanic or sometimes both, and the upper, rigid part of the mantle.
So crust plus upper mantle equals lithosphere, and that makes up the plate.
Correct. And these plates are floating essentially on a hotter, weaker, semi-molten layer below called the asthenosphere. They move horizontally across this layer.
How thick are these plates?
They vary. Oceanic plates might be, say, 5 to 100 kilometers thick, while continental plates are generally thicker, maybe up to 200 kilometers.
And the whole Earth's surface is broken into these moving plates.
That's the picture. There are 7 major plates, like the Pacific Plate, the North American Plate, Eurasian, African, Antarctic, South American, and the India, Australia, New Zealand Plate. And then there are several smaller, minor plates squeezed in between.
So it's the plates that are moving, carrying the continents and ocean floors along with them.
Precisely. And this implies that Pangaea wasn't necessarily a one-off event. The plates have likely been moving, colliding, and breaking apart throughout much of Earth's history, forming and reforming supercontinents.
Okay, so these moving plates must interact with each other at their edges. What happens there?
We classify the boundaries based on how the plates are moving relative to each other. There are three main types.
All right, what's the first type?
Divergent boundaries, that's where plates are moving apart. Mid-Oceanic ridges are the classic example. New crust is formed there as magma wells up.
Like the Mid-Atlantic Ridge. Okay, what's next?
Convergent boundaries. Here, plates are moving towards each other, colliding. What happens next depends on the type of plates.
How so?
If an oceanic plate collides with a continental plate, the denser oceanic plate usually subducts or dives beneath the continental plate. This creates trenches and often volcanic mountain ranges on the continent.
Like the Andes.
Exactly. If two oceanic plates converge, one subducts under the other, forming deep trenches and chains of volcanic islands. And if two continental plates collide...
They're both relatively buoyant, right? So they can't easily subduct.
Right. So they crumple and fold, pushing up massive mountain ranges. The Himalayas are the prime example of a continent collision.
Okay, so divergent apart, convergent together. What's the third type?
Transform boundaries. Here, plates slide horizontally past one another. Crust isn't really created or destroyed, they just grind past each other.
Like the San Andreas Fault in California.
That's a famous example, yes. These transform faults often connect segments of mid-oceanic ridges.
Got it. Divergent, convergent, transform. And we can measure how fast these plates move using those magnetic stripes you mentioned.
Yes, the patterns of magnetic reversals recorded in the ocean crust act like a geological clock or speedometer. By dating the stripes and measuring their width, we can calculate the spreading rate and therefore the plate speed.
Are they all moving at the same speed?
Oh no, it varies quite a bit. Some are very slow, like the Arctic Ridge, maybe less than 2.5 centimeters per year. Others, like the East Pacific Rise, can move much faster, over 15 centimeters per year.
Still incredibly slow by human standards, but geologically significant. So what's actually pushing and pulling these massive plates around? Back to convection currents.
That's still a leading hypothesis, yes. The slow churning of the Earth's mantle, driven by heat escaping from the core and heat from radioactive decay within the mantle itself.
So Arthur Holmes's idea from the 30s was pretty much on the right track.
It seems so. These massive convection cells in the mantle exert drag on the bottom of the plates and also push up at ridges and pull down at subduction zones. It's the engine driving the whole system.
Okay, let's recap plate tectonics. The Earth's lithosphere is broken into rigid plates moving on the asthenosphere. They interact at divergent, convergent, and transform boundaries. This movement, driven by mantle convection, explains continental drift, seafloor spreading, earthquakes, volcanoes, and mountain building. It's the grand unified theory.
Couldn't have put it better myself. It really ties everything together.
Now, let's make this more concrete by looking at one specific plate. The Indian plate. Its journey is quite dramatic, isn't it?
It really is. And very relevant, of course. So the Indian plate today, its northern boundary is that huge collision zone with Eurasia, the Himalayas.
A convergent boundary we talked about.
Exactly. To the east, it dives down at a subduction zone near Indonesia. To the west, the boundary is more complex, involving mountain ranges in Pakistan and spreading centers in the Red Sea. And to the south, it's a divergent boundary, spreading away from the Antarctic plate along an oceanic ridge.
So it's actively interacting on all sides. Where did India start out?
A long, long ways south. Around 225 million years ago, India was actually part of Gondwana land, nestled between Africa, Antarctica, and Australia. It was separated from Asia by a vast ocean called the Tethys Sea.
The Tethys Sea.
Okay. Then, starting around 200 million years ago, as Pangaea broke up, the Indian plate began its solitary northward journey. It moved quite rapidly, geologically speaking.
Across the Tethys Sea towards Asia.
Yes. And the collision with Asia wasn't a single event, but it really began in earnest about 40 to 50 million years ago. That collision is what buckled the crust and pushed up the Himalayas.
An absolutely massive collision. And that's still ongoing, right? India is still pushing into Asia.
It is. That's why the Himalayas are still rising and why the region is so seismically active.
Were there any other major events during India's northward trek?
Oh, yes. Around 60 million years ago, as the plate passed over a hot spot in the mantle, likely near the equator at the time, there was an enormous outpouring of volcanic lava.
That created the Deccan Traps.
Exactly. Huge floods of basalt lava covered a vast area of western and central India. It was a major volcanic episode linked directly to the plates movement.
So we can track its path from being part of Gondwanaland near the South Pole, drifting north, creating the Deccan Traps near the equator, and finally crashing into Asia to build the Himalayas.
That's the journey in a nutshell. We have paleomagnetic data and other evidence suggesting, for instance, that around 140 million years ago, India was way down at about 50 degrees south latitude.
It's an incredible story written on the rocks.
Great.
Okay, quick recap on the Indian plate. Started south as part of Gondwanaland, drifted rapidly north across the Tethys Sea, experienced massive volcanism, Deccan Traps, collided with Asia 40–50 million years ago, forming the Himalayas, and continues to push northward today.
A perfect illustration of plate tectonics in action.
So wrapping up our deep dive today, we've gone from early ideas about drifting continents to the dynamic reality of seafloor spreading and the unifying theory of plate tectonics.
It really highlights how the Earth's surface isn't static at all. It's constantly being reshaped by these powerful internal forces, creating the landscapes we see.
And understanding this framework helps explain so much why earthquakes happen where they do, why volcanoes erupt, how mountain ranges are built. It all connects back to these moving plates.
It absolutely does. It's the foundation for understanding much of physical geography and geology.
So a final thought perhaps for you listening. Given these plates are still moving, relentlessly, centimeter by centimeter, what will the Earth look like millions of years from now?
That's a fascinating question. Will the Atlantic continue to widen? Will Africa collide with Europe, closing the Mediterranean? What new mountains might rise? It puts our current geography into a much longer perspective.
Definitely something to ponder. Well, if this journey through our dynamic Earth has sparked your curiosity, please do subscribe to our YouTube channel, UPSC Mindscape, for more deep dives like this.
Thanks for joining us.
Yes, thanks for tuning in.